Close your eyes for a moment, not to sleep, not yet, just to feel. Feel the breath moving in and out of your body. Feel your chest rising, feel it falling. Feel the quiet hum of your own existence. Now here is a question so simple it almost feels foolish to ask, and yet no scientist on Earth has fully answered it. Why is that breath moving forward? Why does every inhale come after the last exhale? Why does every second follow the one before it? Why does your heartbeat tick onward, always onward, never backward, never sideways, never pausing in the middle to reconsider? You have never experienced yesterday coming after tomorrow. You have never watched a shattered glass reassemble itself from the floor. You have never seen smoke descend back into a cigarette and become unburned tobacco. You have never watched a wave uncrash against a shore. And yet, if you were to write down the laws of physics, the fundamental equations that govern every particle in the universe, something deeply strange appears. Most of those laws work equally well in both directions. Play the equations forward. They describe the universe perfectly. Play them backward. They still work. The mathematics does not care. The physics does not object, and so the mystery deepens. If the laws of nature are symmetric in time, why does time itself move in only one direction? Why do we always remember the past and never the future? Why does every story have a beginning and an end, and never an end and a beginning? What is time really? Is it a river, flowing from some distant mountain of creation toward an endless ocean of dissolution? Is it a dimension of space, something we move through the way we move through a room? Is it an illusion, a story the mind tells itself to make sense of change? Or is it something else entirely? Something so fundamental, so woven into the structure of reality, that it cannot even be separated from the universe itself? These are not idle philosophical questions. They are at the heart of modern physics. They connect thermodynamics and relativity, and quantum mechanics and cosmology. They touch on the origin of the universe, the nature of black holes, and the deepest structure of space and time. And tonight, slowly, carefully, we are going to follow that thread. This is Science for Sleep, and this is the story of time. If you enjoy deep science like this, the kind of science that takes its time, that doesn't rush, that sits with difficult questions until they begin to feel familiar, then subscribe to Science for Sleep. We'll be right here, every night, going deeper. Let's start at the beginning. Or rather, let's start with what we mean when we say beginning. Time is one of the most intimate things in human experience. We feel it constantly. We are soaked in it. We schedule our lives by it. We mourn its passing. We fear its end. And yet, when someone asks us to define it, to say clearly and precisely what time actually is, most of us find ourselves reaching for metaphors rather than definitions. Time is like a river. Time is like a road. Time is what clocks measure. Time is change. These are not bad intuitions, but they are incomplete. And physics asks us to be more careful. The ancient Greek philosopher Aristotle thought of time as the measurement of change. No change, no time. Time, for Aristotle, was not a thing in itself. It was a way of counting how one state of the world became another state. There is something correct in this. We do measure time by change. The pendulum swings. The Earth rotates. The cesium atom oscillates at 9,192,631,770 cycles per second, which is how we define the modern second. But then Isaac Newton came along, and he had a different idea. For Newton, time was absolute. It was a great cosmic backdrop, flowing at a constant rate, independent of anything happening within it, whether the universe were full of matter or completely empty, whether anything moved or changed or existed at all. Time, for Newton, would still tick forward at its steady universal rate. Newton's absolute time felt intuitive for centuries. It matched our experience. It matched our clocks. It allowed physics to make extraordinary predictions. And then, in 1905, a young patent clerk in Bern, Switzerland, dismantled it completely. His name, of course, was Albert Einstein, and we will come to him in great depth as this documentary unfolds. But for now, let's hold this simple idea. What we casually call time has turned out to be far more complicated, far more surprising, and far more beautiful than anyone expected. What does modern physics actually say time is? In the framework of general relativity, Einstein's masterwork completed in 1915. Time is not separate from space. It is woven together with the three spatial dimensions, left, right, forward, backward, up, down, into a single four-dimensional fabric called space-time. You are not moving through space while time passes. You are moving through space-time. And the rate at which you move through the time dimension depends on how fast you are traveling through the space dimensions and on how much gravitational mass is nearby. This is not a metaphor. This is not poetry. This is what the mathematics requires, and it has been confirmed by experiments too numerous to count. But here is the thing that makes physicists pause. Here is the thing that, once you notice it, you cannot unnotice. Space-time, as Einstein described it, is symmetric. The past and the future both exist within the structure of space-time, in a way that treats them with mathematical equality. There is a direction we call the future, and a direction we call the past. But the equations themselves do not declare one to be fundamentally different from the other, and yet your experience of time is anything but symmetric. You remember breakfast but not tomorrow's lunch. You can build a fire, but you cannot unburn wood. You can drop an egg, but you cannot unshatter it. The universe, in your direct and unambiguous experience, has a direction. There is a before and an after. There is a past that is fixed and a future that is open. This asymmetry, this arrow pointing always from past to future, is one of the deepest and most important puzzles in all of science. Why does it exist? That is what we are here to explore. But let's slow down even further. Let's feel the texture of time as we actually experience it, before we start pulling it apart with equations. Think about your memory. Right now, you can remember things that happened earlier today. You can remember things from years ago, but you cannot remember anything from tomorrow. You cannot remember next week. Your memory is a one-way door, and it opens only toward the past. This seems obvious. It seems almost silly to say, and yet it is a profound asymmetry. Why do we only remember the past and not the future? The standard answer is that the past has already happened and the future has not. But that answer, when you press on it, is almost circular. It says, we remember the past because the past is what came before, which is true, but it doesn't tell us why the past is fixed and the future is open. There's another angle. Consider cause and effect. We say that a cause comes before its effect. The gun fires before the bullet arrives. The match strikes before the wood ignites. The wave rises before it falls. Causality, the relationship between causes and their effects, has a direction. Cause comes first, effect comes second. But again, why? The microscopic laws of physics, the rules governing individual particles, don't distinguish between cause and effect. A photon can be absorbed by an atom just as easily as that atom can emit a photon. A particle can scatter off another particle in a way that is perfectly reversible. At the level of individual quantum events, the physics is, to a very good approximation, time-symmetric. And yet, when we zoom out, when we look at the large-scale behavior of billions and trillions of particles, something changes. Something breaks the symmetry. Something gives time its direction. That something has a name. It is called entropy. And it is the protagonist of our story. Let's begin there. Entropy. The word has a reputation. People use it colloquially to mean disorder, chaos, the tendency of things to fall apart. Your messy desk has high entropy. A traffic jam has high entropy. A broken relationship has high entropy. In everyday language, entropy is almost a synonym for mess. This is not entirely wrong, but it is incomplete. And to really understand why time moves forward, we need to understand entropy with real precision. Let us begin with a very simple picture. Imagine a box. Inside the box, there is a thin wall dividing it into two equal halves. On the left side, there are 1,000 gas molecules, tiny, fast-moving particles of, say, nitrogen. On the right side, there is nothing, a vacuum. Now, you remove the wall. What happens? The molecules spread out. They fill the entire box. This is not surprising. This is what gas does. The molecules move around randomly, bouncing off the walls, colliding with each other, and over time, very quickly in fact, they distribute themselves roughly evenly throughout the entire container. Now, here is the question. Why don't the molecules spontaneously gather themselves back onto the left side? You might say, because that would be going backward. because that's not what gas does. But that's not an explanation. That's just a description of what we observe. The real answer lies in counting. Think about it this way. Each molecule can be on the left side or the right side of the box. With 1,000 molecules, how many different arrangements are possible where all of them are on the left? Just one. There is only one arrangement where every single molecule has chosen the left half. But how many arrangements are possible where the molecules are roughly evenly distributed, say between 480 and 520 on each side? An astronomically large number, an incomprehensibly large number, far, far more than one. This is the key insight. When all the molecules are on the left, the system is in a very special, very rare configuration. There are very few arrangements that look like that, but when the molecules are spread out evenly, the system is in one of an enormous number of roughly equivalent configurations. If the molecules are moving randomly, the system will almost always be found in one of the common configurations, not one of the rare ones. The system is overwhelmingly likely to be spread out, not because any law says it must be, not because there's a force pushing the molecules apart, simply because there are so many more ways to be spread out than to be concentrated. This is what entropy measures, not disorder in a vague, colloquial sense. Entropy measures the number of microscopic arrangements, the number of different ways to arrange the particles that correspond to a given macroscopic state. High entropy means there are many, many ways to achieve that state. Low entropy means there are very few ways. And the second law of thermodynamics says this: in an isolated system, entropy tends to increase over time, not because anything forces it to, not because there's a law that says molecules must spread out, simply because there are enormously more high entropy states than low entropy states. And random motion will almost always take you from a rare arrangement to a common one, rather than the other way round. This is the second law. It is sometimes called the most universal law in physics. It applies to gases and liquids and solids. It applies to living organisms and to galaxies. It applies in some sense to the entire observable universe. And it is the reason, or at least a very large part of the reason, that time has a direction. Let me explain. When the gas molecules are all on the left side of the box, the entropy is low. There are very few arrangements that look like that. When the molecules spread out, the entropy increases. There are far more arrangements that look like that, and the process is irreversible in practice. Because the probability of the molecules spontaneously returning to the left side is not zero. It's just so vanishingly small that in the lifetime of the universe you would not expect it to happen even once. This is what physicists call a thermodynamic irreversibility. The process goes in one direction, not because going the other direction is forbidden, but because it is so extraordinarily unlikely as to be, for all practical purposes, impossible. And here is the connection to the arrow of time. The direction of increasing entropy, the direction in which ordered, low entropy states become disordered, high entropy states, corresponds to what we call the future. The future is the direction of increasing entropy. The past is the direction of lower entropy. This is a deep idea. Let it settle. When you look at a glass of water with an ice cube in it, you know immediately that the ice will melt. You know the future. The ice disappears, the water becomes uniformly cool, and eventually it all reaches the same temperature. This is entropy increasing, the highly ordered, separated state. Ice and water, cold and less cold, gives way to a more disordered, uniform state. If you were shown a video of ice forming spontaneously in a glass of water at room temperature, you would know immediately that the video was playing backward, not because the physics forbids it. The individual molecular collisions are all reversible, but because the process would require entropy to decrease. And that is so extraordinarily improbable that it never happens. Your brain is a detector of entropy. You know which way time flows by detecting which direction entropy increases. You know the egg falls and breaks. You know the smoke rises and disperses. You know the fire burns down, not up from ashes. These are all entropy increasing, and entropy always increases in the direction we call forward in time. But wait. Here is a question worth pausing on. Why was the entropy low in the first place? This is not a trivial question. If entropy always increases, if the second law is universal, then why is the universe not already in its highest entropy state? Why is there still ice in the glass? Why are there still stars? Why are there still living, breathing organisms who can think about entropy? The answer takes us all the way back to the beginning of time. The universe started in an extraordinarily low entropy state. The Big Bang, or more precisely, the very early universe, was in a configuration of astonishing order, not the kind of order you might imagine from the word. The early universe was a hot, dense, featureless plasma, which doesn't sound orderly at all. But from the point of view of entropy, the early universe was extraordinarily special. Gravity was not yet doing its work of pulling matter into clumps. The matter was spread almost perfectly uniformly, and a uniform distribution of matter, from a gravitational standpoint, is actually a low entropy state, because gravity wants to pull things together into structures. Stars, galaxies, black holes. The more clumped things become under gravity, the higher the gravitational entropy. So the early universe had very low entropy. Everything since then, every star that formed, every galaxy that assembled, every planet that cooled, every ocean that filled, every creature that lived and died, has been entropy increasing, has been the universe moving from that initial state of extraordinary order toward its eventual maximum entropy, which physicists call the heat death of the universe, a state of perfect, featureless equilibrium where nothing changes and nothing happens. The arrow of time, the direction from past to future. The reason your breakfast comes before your dinner and your birth comes before your death. All of this traces back, in the view of modern thermodynamics, to that initial low entropy state of the Big Bang. We are living in the long, slow exhale of an extraordinarily ordered beginning. And the direction of that exhale, the direction entropy flows, is what we call forward in time. This is beautiful. But it's also a little vertiginous, because it raises another question. Why did the Big Bang start in such a low entropy state? That question we will come to. But first, let's go deeper into the thermodynamics. Let's meet the man who first understood all of this. His name was Ludwig Boltzmann. He was an Austrian physicist working in the second half of the 19th century, and he was one of the most brilliant and most tragic figures in the history of science. Boltzmann's great insight, the insight that changed everything, was to connect entropy, which was a concept from thermodynamics, with the microscopic world of atoms and molecules. At the time Boltzmann was working, the existence of atoms was not universally accepted. Many prominent physicists and philosophers of science believed that atoms were a convenient fiction, a useful mathematical tool perhaps, but not a description of physical reality. Boltzmann believed passionately that atoms were real. He devoted much of his life to proving it. In the course of that work, he developed what is now called statistical mechanics, a framework for understanding the behavior of large collections of particles by thinking about the statistics of their possible arrangements. And out of that framework came his famous formula, now inscribed on his tombstone in Vienna, S=eq log W. It is one of the most important equations in all of physics. Let me tell you what it means. S is entropy. W is what Boltzmann called the number of microstates, the number of different microscopic arrangements of all the particles in a system that would produce the same macroscopic appearance. K is a tiny number called Boltzmann's constant, which connects the microscopic and macroscopic worlds. The equation says, entropy is proportional to the logarithm of the number of microstates. When there are many, many ways to arrange the particles, when W is large, entropy is high. When there are very few arrangements, when W is small, entropy is low. This is exactly what we said before about the gas in the box. But now it has a precise mathematical form, and the logarithm is important. It means that entropy grows slowly even as the number of microstates grows astronomically fast. This makes the mathematics tractable. The beauty of Boltzmann's formula is that it gives entropy a physical meaning grounded in probability. Entropy is not some mysterious property of matter. It is simply a measure of how many ways things can be arranged. High entropy means you are in a common, ordinary state. Low entropy means you are in a rare, special state. And the second law of thermodynamics, entropy tends to increase, is now not a fundamental law at all. It is a statistical statement. Entropy tends to increase because there are almost always far more high entropy states than low entropy states, and random evolution tends to take you from rare states to common states. This is a profound shift in how we understand physical law. Newton's laws of motion are deterministic. If you know the positions and velocities of all the particles, you can calculate exactly where they will be at any future time. These laws have no preferred direction in time. If you reverse all the velocities, the particles will trace backward through their exact trajectories. The laws are perfectly time reversible. Boltzmann's statistical mechanics is different. It deals with what typically happens, what happens on average, what happens to overwhelmingly high probability, and typically, on average, with overwhelmingly high probability, entropy increases. Here is the strange and wonderful thing. Boltzmann realized that his second law was not absolute. It was not a guarantee. It was a statement of extreme probability. In principle, in the mathematical framework, it was possible for entropy to spontaneously decrease. A cup of cold coffee could spontaneously grow hot. A broken glass could spontaneously reassemble. The probability is just so unimaginably small, so many orders of magnitude below anything we could ever observe, that it is operationally indistinguishable from impossible. To give you a sense of the numbers, the probability of the molecules of gas in a room spontaneously concentrating into one corner is not 0, but it is something like 10 to the power of negative 10 to the power of 23. That is a number so small that if you tried to write it out, the number of zeros would exceed the number of atoms in the observable universe by an incomprehensible margin. For all practical purposes, entropy does not decrease. The arrow of time is not violated. The second law holds, but Boltzmann's insight reveals something important. The arrow of time is not a fundamental asymmetry of the laws of physics. It is an emergent property of the statistics of large numbers. It arises because we live in a universe with an enormous number of particles. And the second law is just what happens when you let probability do its work at that scale. This leads to a haunting thought experiment that Boltzmann himself wrestled with. If the laws of physics are time-symmetric, and if the universe has been around long enough, then in principle, any state, including a very low entropy state, could arise spontaneously by a random fluctuation. Given infinite time, the gas molecules would eventually all find themselves back in one corner of the box. Given enough time, a brain could spontaneously assemble itself from the random motion of particles, complete with false memories of a past that never existed. Physicists call this a Boltzmann brain, a self-aware observer arising from a random entropy fluctuation, persisting for just a moment before dissolving back into disorder. Now, Boltzmann brains are not meant to be taken literally as a prediction. They are a philosophical probe, a way of testing whether our understanding of entropy and time is consistent. If the universe is in some eternal equilibrium state, and low entropy fluctuations occur randomly, then Boltzmann brains would be far more common than real brains that evolved over billions of years of cosmological history, because a fluctuation big enough to produce a single brain-like structure is far more likely than a fluctuation big enough to produce an entire organized universe. The fact that we seem to exist in a large, organized, cosmologically evolving universe, rather than as isolated Boltzmann brains, suggests that our universe is not in equilibrium. It suggests that the low entropy of the early universe is a real feature of our cosmological history, not just a random fluctuation. This is one of the reasons cosmologists take so seriously the question of the initial conditions of the Big Bang. The low entropy of the early universe is not something to take for granted. It demands an explanation, but we are getting ahead of ourselves. Let us pause here and think about what we have established. Time has a direction. That direction is the direction of increasing entropy. Entropy is a measure of the number of ways things can be arranged. The second law of thermodynamics says entropy increases because there are almost always more high entropy states than low entropy states. The early universe had very low entropy. We are in the long process of that entropy increasing. These are the thermodynamic foundations of the arrow of time. Now, there is a question worth sitting with for a moment before we continue. If time ran backward, if right now everything in the universe reversed, would you notice? Think about it carefully. If every particle in the universe reversed its direction of motion at this instant, and time began running backward, then entropy would start decreasing. Ice would form in warm water, broken glasses would reassemble, the smoke from fires would condense back into wood. Would you notice? Well, your brain is also a physical system. Your memories are encoded in the physical arrangement of neurons and synapses. If time reversed, your memories would unencode in the reverse direction. You would not remember the moment of reversal. You would experience yourself moving backward through events, But from your subjective perspective, which is itself just a physical process, it would feel exactly like moving forward. This is deeply strange. It suggests that the experience of time's forward motion is not separate from the physical process of entropy increasing. Your sense of time passing, your feeling of moving from past to future, may itself be a consequence of entropy. Your memories are records of lower entropy pasts. Your anticipation of the future is an openness toward higher entropy states. The direction of your psychological experience of time aligns exactly with the direction of thermodynamic entropy increase. Memory and entropy are, in a deep sense, the same thing. And on that thought, if you're enjoying this journey through time and entropy, if this slow unfolding of ideas feels right for the way you like to learn, subscribe to Science for Sleep. There's much more to come, and we go deeper every night. Let's zoom all the way in. Let's go down to the level of individual particles and ask, what do the fundamental laws of physics say about time? The answer is surprising, and it connects to everything we have been discussing. Consider Newton's second law. Force equals mass times acceleration. If you reverse time, if you replace t with negative t in the equation, the law still holds. Acceleration, which is the rate of change of velocity, becomes the rate of change of the reversed velocity. The mathematics is unchanged. Newton's laws are time-symmetric. Maxwell's equations, which describe electricity and magnetism and light, are also time-symmetric. If you reverse the direction of time, an electromagnetic wave traveling to the right would become an electromagnetic wave traveling to the right, or to the left, depending on your point of view. But the equations themselves remain valid in either direction. The Schrödinger equation of quantum mechanics, which governs how quantum states evolve, is also time-symmetric for the most part. Play it forward, you get the future state of the quantum system. Play it backward, you get the past state. Either way, the equation is satisfied. In fact, almost all of the fundamental equations of physics share this property. They are time reversal invariant. They do not care which direction time flows. The one notable exception, and it is a small but important exception, involves certain interactions between subatomic particles called the weak nuclear force. There are specific rare processes involving particles called kaons and b-mesons that are slightly asymmetric in time. This is called CP violation, a subtle asymmetry in how particles and antiparticles behave. Physicists discovered it in the 1960s and have been studying it ever since. This weak CP violation is real, and it is relevant to certain cosmological questions, including why the universe contains more matter than antimatter. But it is far too small, far too restricted to certain rare particle decays to account for the overwhelmingly obvious arrow of time that we experience in everyday life. The irreversibility of a breaking egg has nothing to do with kaon physics, so the puzzle stands. The laws are symmetric, the experience is not, and the answer, as we have been developing, is statistical. It is not written into the laws themselves. It is written into the initial conditions. Let me say that again because it is important. The arrow of time is not a consequence of the laws of physics being asymmetric in time. The laws are essentially symmetric. The arrow of time is a consequence of the initial conditions of the universe, specifically the fact that the universe began in a very low entropy state. Given those initial conditions, and given the symmetric laws, entropy increases in the direction we call forward. This direction becomes what we experience as the future, and the direction of lower entropy, the direction we cannot go, becomes what we call the past. This is a remarkable realization. The direction of time, the difference between past and future, is not encoded in the laws of physics. It is encoded in the history of the universe. Now, there is a beautiful thought experiment that illustrates this. It is sometimes called the movie test. Imagine you are shown a short film clip of some physical process. Your task is to determine whether the film is playing forward or backward. If the clip shows a single billiard ball rolling across a table and bouncing off a cushion, you cannot tell. The physics is perfectly reversible at this level. The ball would look just as natural rolling in either direction, but if the clip shows a rack of 15 billiard balls being broken by the cue ball, exploding outward in all directions, you know immediately which direction is forward. The moment of collision and explosion is forward. The moment of all the balls spontaneously gathering themselves back into a perfect rack, with the cue ball reversing into them, is backward. Your brain knows this instantly. Why? Because the explosion corresponds to entropy increasing. One organized arrangement, the rack, becomes many scattered arrangements, and the spontaneous re-racking corresponds to entropy decreasing, which essentially never happens. The movie test is a test for entropy. Any process where entropy clearly increases looks natural when played forward and absurd when played backward. Any process that is truly microscopically reversible, like the single billiard ball, looks equally natural in both directions. This gives us a practical definition of the arrow of time. The direction of time is the direction in which entropy increases. Full stop. Now there is one more subtlety here that is worth addressing carefully. We said that the laws of physics are time-symmetric, but there is a process in quantum mechanics that seems to break this symmetry: the measurement, or the collapse of the wave function. In quantum mechanics, before a particle is measured, it exists in what is called a superposition, a combination of multiple possible states simultaneously. When a measurement is made, the superposition collapses to a single definite outcome. This process, the collapse, is irreversible. You cannot uncollapse a wave function. The measurement outcome is recorded. The information is spread into the environment, and the process cannot be undone. This sounds like the collapse is a source of the arrow of time, and some physicists do believe this. But the situation is complicated by the fact that there is no universal agreement among physicists about what wave function collapse actually is, or whether it is a fundamental process or an emergent one. Different interpretations of quantum mechanics treat this differently. In the Copenhagen interpretation, collapse is a real, irreversible process that happens when a measurement is made. In the many worlds interpretation, there is no collapse at all. The wave function always evolves according to the Schrödinger equation, and apparent measurement outcomes are just different branches of a constantly splitting universal wave function. In this picture, the arrow of time in quantum mechanics is again just a statistical consequence of entropy. The quantum foundations of the arrow of time are still an active area of research, and we will return to the quantum perspective in more depth shortly. For now, let's carry the following understanding forward. The microscopic laws are time-symmetric. The macroscopic experience of time is not. The bridge between these two facts is entropy, specifically the initial low entropy of the universe, which sets up the conditions for entropy to increase in one direction, which we call the future. And as we go deeper, as we bring in Einstein's theory of relativity, as we look at what happens near black holes, as we examine the very structure of space-time, this picture will become richer and more profound. But first, let me ask you something. Think about your own past. Think about a specific memory, something from years ago, something vivid. Why do you remember it as the past rather than the future? What is the difference, in physical terms, between a memory of something that happened and an anticipation of something that will happen? Both involve a brain state. Both involve neurons and synapses and electrochemical signals. But one is fixed, unchangeable, settled, and one is open, uncertain, contingent. The fixed quality of the past, the way it sits there in your mind as something that definitely happened, is itself a thermodynamic phenomenon. When an event occurs, it leaves traces. It increases entropy in its local environment. The scattering of information into the surroundings is irreversible in the thermodynamic sense. And those traces, those irreversible imprints on the world, are what we call the past. Your memories are not just psychological, they are thermodynamic records. The past is not just gone, it is recorded in the high entropy configuration of the universe. This is why we feel time moving forward. Not because the laws of physics decree it, but because we are living in an entropy-increasing universe, and our minds, which are physical systems embedded in that universe, are themselves entropy-increasing processes. We are the universe becoming aware of its own thermodynamic directionality. We have been exploring time from the perspective of thermodynamics, from entropy and the second law. Now let's approach time from a completely different direction. Let's talk about relativity, and let's begin with a small act of imagination. Imagine you are standing on a train platform, watching a train go by at very high speed. On the train, there is a passenger holding a clock, and here is what Einstein's special theory of relativity tells us. That clock is running slow, not because there is anything wrong with the clock, not because the train vibrates it, but because of something deep and fundamental about the nature of time itself. Moving clocks run slow. Moving systems age more slowly. This is not a mechanical effect. It is an effect of the geometry of space-time. This phenomenon is called time dilation, and it is real. It has been measured countless times with extraordinary precision. One of the most elegant early tests involved muons, subatomic particles created when cosmic rays strike the upper atmosphere. Muons are unstable. They decay after an average of about 2.2 microseconds, about 2 millionths of a second. When they are created in the upper atmosphere, about 10 to 15 kilometers above the surface, traveling at nearly the speed of light, they should decay long before reaching the ground. At the speed of light, they would travel only about 660 meters in 2.2 microseconds. They shouldn't make it, but they do. They arrive at the surface in large numbers. Why? Because from our frame of reference on the ground, the muons' internal clocks, which determine how quickly they decay, are running slow due to time dilation. The muons experience much less time during their journey than we do. Their 2.2 microsecond lifetime, dilated by their relativistic speed, stretches into enough time to cover the full 10 to 15 kilometers. From the muon's perspective, from the reference frame moving with the muon, something different but equally valid is happening. The distance between the upper atmosphere and the ground is contracted. The muon doesn't experience much time passing because the distance it has to travel is dramatically shortened by length contraction. The other key consequence of special relativity: both descriptions are correct. Both are valid frames of reference, and they agree on the outcome. The muon reaches the ground. This is what special relativity teaches us. There is no universal, absolute time ticking at the same rate for everyone. Time is relative. The rate at which time passes depends on how fast you are moving. Two observers in relative motion will measure time differently, and both will be correct within their own reference frames. This is disorienting. It shakes something in our intuition about what time is. We are accustomed to thinking of time as a shared backdrop, the same time for everyone everywhere. Relativity tells us this is wrong, but here is something crucial for our discussion of the arrow of time. Even though relativity changes the rate at which time passes, it does not change its direction. Every observer, in every reference frame, still experiences time moving from their personal past to their personal future. Special relativity mixes space and time together, but it does not allow time to reverse. The direction of time, the arrow, is preserved even within the relativistic framework. What changes is how much time passes, not which way it points. Now let's go from special relativity to general relativity, because this is where things become even more extraordinary. Einstein's special theory of relativity, published in 1905, dealt with reference frames moving at constant velocities relative to each other. His general theory of relativity, completed in 1915, extended this to include acceleration and gravity, and the result was revolutionary. In general relativity, gravity is not a force. It is a curvature of space-time. Mass and energy, anything with mass, anything with energy, curves the fabric of space-time around it, and other objects, moving through that curved space-time, follow the paths dictated by the curvature. What we call the force of gravity is actually the geometry of space and time. And here is the key consequence for our story. Just as high velocity causes time dilation in special relativity, strong gravity causes time dilation in general relativity. The closer you are to a massive object, the deeper you are in a gravitational field, the more slowly time passes for you, relative to someone far away. This effect has been measured with remarkable precision. The GPS satellites orbiting the Earth are high above the planet's surface, in a weaker gravitational field than we experience at ground level. As a result, their clocks run faster than clocks on Earth's surface. If the GPS system did not correct for this effect, both the special relativistic slowing due to the satellite's orbital speed and the general relativistic speeding due to their altitude, the position errors would accumulate at a rate of several kilometers per day, and the entire GPS network would become useless within hours. General relativistic time dilation is not theoretical. It is practically important. It is part of the technology you use every day. Now, this is remarkable. Time passes at different rates in different gravitational environments. Time near a massive object passes more slowly than time far away, and as the gravitational field becomes more extreme, as we approach what are called black holes, the time dilation becomes more and more dramatic. Near a black hole, time dilation becomes so extreme that it takes us directly to the frontier of what physics understands. And we will go there. That is coming soon. But first, let's put the relativistic picture together with the thermodynamic one, because they connect in a beautiful and somewhat surprising way. Relativity tells us that time is not absolute. Its rate varies. Its measurement depends on your motion and your location in a gravitational field. Different observers can measure different amounts of time between the same two events, but entropy is absolute. The number of microstates is a real physical quantity. The direction of entropy increase is the same for all observers. Even though different observers might measure time at different rates, they will all agree that entropy increases in the direction they each call the future. In other words, even within the relativistic, observer-dependent framework of spacetime, the thermodynamic arrow of time remains consistent. All observers agree that the future is the direction of increasing entropy. This is reassuring. It suggests that even as we dig deeper into the relativistic structure of spacetime, even as time becomes more complicated and more relative, the thermodynamic arrow remains as a consistent, observer-independent anchor for the direction of time. And if you are finding this journey both fascinating and restful, if this particular blend of deep science and unhurried narration is what you come to Science for Sleep for, then take a moment to subscribe. We will always be here, going slowly, going deeply. Now let's go deeper into the geometry of spacetime, because there is a view of time in relativity that is profoundly unsettling to many people, and profoundly beautiful to others, and we should sit with it carefully. It is called the block universe. Sometimes it is called eternalism, and it is the view that the past, present, and future all exist equally, as fixed features of a four-dimensional space-time structure. In this picture, time is not a flow, it is not a river, it is a dimension, and events, whether they happened yesterday, are happening now, or will happen tomorrow, all exist as equally real points in the four-dimensional block of spacetime. The sense that time flows, the feeling of the present moment, the experience of now, these, in the block universe view, are features of consciousness, not features of physical reality. The universe doesn't move through time. The universe is all of time, spread out in four dimensions, and we experience a cross-section of it as the present. This is a view that many physicists find natural, because general relativity treats spacetime as a single unified geometric object. Past, present, and future are all part of that object. The equations of general relativity do not privilege any particular moment as specially real, but this view raises an immediate and profound question about the arrow of time. If all moments of time exist equally, if the past and the future are equally real features of the block universe, then in what sense is the future open? In what sense is the present special? In what sense does time flow? And crucially, if the future is already there, already written into the structure of spacetime, then is free will possible? Is there any meaningful sense in which the future is undetermined? These are deep questions that touch on philosophy and physics in equal measure. We should be honest that they are not fully resolved. Some physicists take the block universe view very seriously. They argue that the feeling of time flowing is an illusion, a cognitive artifact, a feature of how brains process information, not a feature of physical reality. In this view, you are moving through a static four-dimensional structure, not through a dynamic, evolving universe. Other physicists, and many philosophers of time, resist this view. They argue that quantum mechanics introduces genuine indeterminacy into the future, and that this indeterminacy means the future is not yet written in any meaningful sense. The future is not a fixed feature of a block universe. It is genuinely open, genuinely undetermined, until the quantum events that create it have occurred. Still others propose a third view, sometimes called the growing block universe. The past and present are real, fixed features of spacetime, but the future is not yet real. Time is a block that is perpetually growing, with new moments of reality being added as they occur. We do not need to resolve this debate tonight. These are among the most difficult questions in the philosophy of physics, and brilliant people disagree about them. But it is worth knowing that they exist, because they reveal that our understanding of time, even with all of modern physics at our disposal, is still incomplete. What we do know, and what is not seriously disputed, is this. Within the structure of spacetime, as described by general relativity, there is a concept called the light cone, and the light cone gives us a local, precise version of the arrow of time. Every event in space-time, every point in the four-dimensional structure, has a light cone associated with it. The light cone is defined by the paths that light would take through space-time from that event. Since nothing can travel faster than light, the light cone defines which other events can causally influence, or be causally influenced by, the given event. The future light cone contains all events that could, in principle, be reached from the given event by something traveling no faster than light. The past light cone contains all events that could, in principle, have sent a signal to the given event by something traveling no faster than light. And everything else, everything outside the light cone, is causally disconnected from the event in question. The light cone defines a local direction of time, from past light cone to future light cone. This direction is set by the causal structure of spacetime, and it aligns in a beautiful way with the thermodynamic direction of entropy increase. In a universe with low entropy initial conditions, the direction of increasing entropy is always the future direction of the light cone. The two concepts of time, the causal and the thermodynamic, point in the same direction. They reinforce each other. They are, many physicists believe, deeply connected. Now there is one more concept from space-time structure that we need before we move on to our discussion of black holes. It is the concept of geodesics. In flat space, in the absence of gravity, objects in motion travel in straight lines. This is Newton's first law. In curved space-time, in the presence of gravity, objects in free fall travel along what are called geodesics, the closest thing to a straight line in curved space. Geodesics are the paths of least action through spacetime. What is beautiful about geodesics is that they represent a kind of extremal path through spacetime. They maximize the proper time, the time actually experienced by the traveler, between two events. Among all the possible paths through spacetime between two events, the geodesic is the one that takes the most time. This has a strange consequence. If you want to age as slowly as possible, if you want to experience as little time as possible between two events, you should deviate from a geodesic. You should accelerate. You should burn fuel and travel in a complicated path through spacetime. This is the twin paradox of special relativity. If one twin stays at home and the other travels at high speed through space, the traveling twin ages less when they reunite, not because the traveler somehow cheated time, but because they traveled a non-geodesic path through spacetime. And non-geodesic paths through spacetime correspond to less proper time. The geometry of spacetime determines how much time you experience, and the direction of that time, toward the future, is determined by thermodynamics, geometry and thermodynamics, curvature and entropy. These two great pillars of modern physics are both in their own ways telling us the same thing. Time has a direction, and that direction is from low entropy to high entropy, from the ordered beginning to the disordered future. And now we come to the most dramatic chapter in our story of time. We go to the places where time is most distorted, most extreme, most revealing. We go to black holes. A black hole is a region of spacetime where gravity has become so extreme that nothing, not matter, not light, not any signal or information can escape. The boundary of this region is called the event horizon. It is one of the most profound concepts in all of physics. To understand what black holes do to time, we need to think carefully about general relativistic time dilation. We established earlier that the closer you are to a massive object, the more slowly time passes for you. A clock at sea level runs slightly slower than a clock at the top of a mountain, because it is deeper in Earth's gravitational field. The difference is tiny, a few nanoseconds per day, but it is real and measurable. Now imagine replacing Earth with something far more massive, a neutron star, whose surface gravity is billions of times greater than Earth's, or a black hole, where gravity becomes infinite, in the classical description, at the singularity. As you approach the event horizon of a black hole, the gravitational time dilation becomes more and more extreme. For a distant observer watching you fall toward a black hole, your clock appears to run slower and slower. Your image becomes more and more redshifted. The light from you is losing energy as it climbs out of the gravitational field. And as you approach the event horizon, from the distant observer's perspective, you appear to slow down asymptotically. You seem to hover just above the horizon, frozen in time, growing dimmer and more redshifted, until your image fades entirely. From the perspective of the distant observer, you never quite cross the event horizon. You appear frozen there forever, but from your own perspective, from your personal frame of reference as you fall, something completely different happens. You cross the event horizon without any special sensation. If the black hole is massive enough, you might not even notice the moment of crossing. You are still experiencing time as flowing forward normally. Your watch still ticks. Your heart still beats. You still feel time moving from your past to your future. And yet, once you have crossed the event horizon, something has changed irrevocably. The singularity at the center of the black hole lies in your future. Not in your future spatially, not somewhere in the space ahead of you, but in your future temporally. You cannot avoid the singularity, not because it is in a particular direction in space, but because it is in the future direction of all paths through space-time inside the horizon. This is one of the most extraordinary facts about black holes. Inside the event horizon, the singularity is not a place. It is a time. It is your future. And just as you cannot avoid the future outside a black hole, you cannot choose not to age, not to continue into the next moment. Inside a black hole, you cannot avoid the singularity. It is literally your future. The geometry of space-time inside a black hole is so warped that what we normally think of as a spatial dimension, the dimension pointing toward the singularity, has become time-like, and what we normally think of as a future direction, the direction of increasing time, points toward the singularity. Time inside a black hole is strange, profoundly strange, and at the singularity itself, the equations of general relativity break down entirely. The curvature of space-time becomes infinite, and our current theories cannot tell us what happens there. Many physicists believe that a quantum theory of gravity, an as yet undiscovered framework that combines general relativity and quantum mechanics, would resolve the singularity and tell us what happens at the center of a black hole. This is one of the great unsolved problems of modern physics. But let's stay just outside the event horizon for a moment, because there is something else remarkable here. Something that connects black holes to entropy and the arrow of time in a profound way. In the early 1970s, a young physicist named Jacob Bekenstein made a startling proposal. He suggested that black holes have entropy. This might not sound radical until you think about what entropy means. It is a measure of the number of microscopic configurations of a system. For a black hole, which classically has no internal structure visible from outside, it is described entirely by its mass, its electric charge, and its angular momentum. The idea that it has entropy raised deep questions. Bekenstein proposed that the entropy of a black hole is proportional to the area of its event horizon, not the volume, the area. This is deeply strange because in ordinary thermodynamics, entropy is proportional to volume. But for a black hole, it scales with area. Shortly after, Stephen Hawking, in one of the most remarkable calculations in the history of theoretical physics, showed that black holes are not completely black. When quantum effects are taken into account near the event horizon, black holes slowly emit radiation. This radiation is now called Hawking radiation. The temperature of a black hole is inversely proportional to its mass. Small black holes are hotter than large ones, and as a black hole radiates, it loses mass, becomes hotter, radiates more, loses more mass, and eventually, over an astronomically long time, evaporates entirely. Hawking radiation connects thermodynamics, quantum mechanics, and general relativity in a single phenomenon. It is a bridge between our three great pillars of modern physics, and it has led to one of the deepest puzzles about time and information in all of physics, known as the black hole information paradox. Here is the paradox. When you throw something into a black hole, you lose access to information about it. From outside the horizon, you cannot tell what went in. All you know is the mass, charge, and spin of the black hole. Whether you threw in a book, or a shoe, or a quantum of radiation, the result looks the same from outside. Now, Hawking radiation eventually evaporates the black hole. The radiation that comes out appears to be completely random. It contains no information about what fell in. So after the black hole has evaporated, is the information about the original matter simply gone? In quantum mechanics, the evolution of quantum states is unitary, which means it is completely reversible in principle. Information is never destroyed. It is preserved. even if it becomes scrambled and practically inaccessible. But if information falls into a black hole and is destroyed when the black hole evaporates, that would violate unitarity. It would be a fundamental breakdown of quantum mechanics. This paradox has been one of the most intensely studied problems in theoretical physics for the past 50 years, and recent work, particularly developments involving the so-called holographic principle and the study of quantum entanglement between Hawking radiation and the interior of the black hole, suggests that information is preserved, that the radiation, while appearing random, actually contains extremely scrambled information about everything that fell in. But this resolution is still being worked out, and many details remain unclear. What the black hole information paradox tells us, for our purposes, is this. At the deepest level, at the interface of quantum mechanics and general relativity, the question of time and its direction is still alive. Information, unitarity, entropy, the arrow of time, these are all connected, and their connection at the extremes of physics is still being discovered. Hawking himself spent years on this problem. His final view before his death in 2018 was that information is preserved, that the evolution of a black hole, including its eventual evaporation, is in principle reversible, even though it is practically irreversible in any meaningful sense. This is a beautiful echo of the statistical nature of the second law. Thermodynamic irreversibility and quantum mechanical reversibility can coexist. The process is reversible in principle but irreversible in practice, because the information becomes so scrambled, so thoroughly mixed into the radiation, that recovering it would require capabilities far beyond anything physically achievable. The arrow of time, even at the extreme edge of black holes, is preserved by the same logic as everywhere else, not by a fundamental asymmetry in the laws, but by the overwhelming improbability of going the wrong way. We have talked about thermodynamics. We have talked about relativity. Now let's look at the quantum perspective on time, because quantum mechanics has its own strange relationship with the arrow of time. In quantum mechanics, the state of a system is described by a wave function, a mathematical object that encodes the probabilities of all possible measurement outcomes. The wave function evolves according to the Schrödinger equation, which, as we mentioned, is time-symmetric. Play it forward, play it backward, both are valid solutions. But there is a process in quantum mechanics that seems to break this symmetry. Measurement. When a quantum system is measured, its wave function collapses from a superposition of many possible states to a single definite outcome. This collapse appears irreversible. Once the measurement has been made and the outcome recorded, the superposition is gone. You cannot uncollapse a wave function. Why does measurement cause collapse? And why is it irreversible? These are the deep questions of quantum foundations, and different interpretations of quantum mechanics answer them very differently. In the Copenhagen interpretation, the oldest and most widely taught interpretation, collapse is a fundamental, irreversible process that occurs whenever a quantum system interacts with a classical measuring device. The measurement is the boundary between the quantum and classical worlds, and crossing that boundary is irreversible. But many physicists are uncomfortable with the Copenhagen interpretation because it introduces an ill-defined boundary between quantum and classical, and because it treats measurement as something special without explaining why measurement is special. The many worlds interpretation, proposed by Hugh Everett in 1957, takes a different approach. In this view, there is no collapse. The wave function always evolves according to the Schrödinger equation. When a measurement is made, the universe splits into branches, one for each possible measurement outcome. All outcomes occur in different branches of the universal wave function. In the many worlds interpretation, the arrow of time and the apparent irreversibility of measurement are both consequences of decoherence, the process by which quantum superpositions become practically indistinguishable from classical mixtures when a quantum system interacts with a large environment. Decoherence is real, and it is extremely fast. For macroscopic objects of everyday scale, decoherence occurs so rapidly that the quantum superpositions become unobservable on timescales far shorter than any measurement we could make. By the time we could in principle detect the superposition, it has already decohered, and decoherence is irreversible in the same statistical sense that thermodynamic processes are irreversible. When a quantum system becomes entangled with an environment containing an enormous number of particles, the information about the superposition becomes spread throughout the environment. Recovering it would require manipulating every particle of the environment simultaneously, which is, in practice, impossible. So the quantum mechanical arrow of time, the apparent irreversibility of measurement and decoherence, is once again a statistical irreversibility, not a fundamental one. It traces back to the same source as the thermodynamic arrow, the low entropy initial conditions of the universe. But there is something deeper here, something that physicists call the emergence of the classical world. The universe began in a quantum state. The early universe, on the smallest scales, was governed by quantum mechanics. As it expanded and cooled, as quantum fluctuations in the density of matter became the seeds of galaxies and stars and planets, the quantum world gave birth to the classical world through the process of decoherence. The classical laws of physics, Newton's laws, thermodynamics, the smooth spacetime of general relativity, all emerge from the quantum substrate as a consequence of decoherence and the interaction of quantum systems with large environments. And the arrow of time, the second law of thermodynamics, the direction from past to future, is itself an emergent property of this quantum substrate, arising from the interplay of quantum decoherence and the low entropy initial conditions. We are built from quantum mechanics, living in a classical world that emerged from it. And our experience of time, the flowing, irreversible river of moments, is a consequence of the statistical behavior of an incomprehensibly large number of quantum events, all pointing in the same entropic direction, because they all started from the same extraordinarily ordered beginning. This is one of the most beautiful stories in all of science. And like all truly beautiful scientific stories, it ends not with a period, but with more questions. What determined the initial quantum state of the universe? Why did the Big Bang produce such low entropy? Is there a deeper law, beyond the second law, that explains the special initial conditions? These are the frontier questions. Let's approach them carefully. We keep returning to this point. The arrow of time traces back to the low entropy of the early universe. But why was the early universe in such a low entropy state? This is not a question that thermodynamics can answer. Thermodynamics describes how entropy evolves from whatever initial conditions it starts with. It does not tell us why the initial conditions were what they were. This is the question of cosmological initial conditions, and it is one of the deepest open questions in all of physics. Let's think about what the early universe actually looked like. Approximately 13.8 billion years ago, the observable universe was in a state of extraordinary density and temperature. In the first fraction of a second, the first hundredth of a second, the first billionth of a second, the first 10 to the negative 43 seconds, which is called the Planck time, the density and temperature were so extreme that our current physics cannot reliably describe them. But in the very early universe, just fractions of a second after the Big Bang, the matter was in a nearly uniform state. Not perfectly uniform. There were tiny fluctuations, tiny ripples in the density, at the level of 1 part in 100,000. These fluctuations were quantum in origin, amplified by a process called cosmic inflation. From a purely thermal perspective, this might sound like a high entropy state, hot, featureless, uniform, and in some sense, from the perspective of the matter alone, it is. The thermal equilibrium is a maximum entropy state for a fixed amount of energy in a box. But here is the subtle and crucial point. The early universe was not in a box. It was not in thermal equilibrium with respect to gravity. Gravity wants to pull matter together. Gravity wants to form clumps, stars, galaxies, black holes, and a perfectly uniform distribution of matter. While it is thermal equilibrium with respect to ordinary particle physics, is a very low entropy state with respect to gravity, the total entropy that the universe could in principle have. If all its matter were concentrated into black holes, the maximum possible entropy states is incomparably larger than the entropy of the early universe. The early universe, while hot and seemingly featureless, was in an extraordinarily special gravitational configuration. As the universe aged, gravity did its work. Matter clumped into galaxies. Galaxies assembled into clusters. Stars formed, burned their nuclear fuel, and died, sometimes in spectacular supernova explosions that enriched the universe with heavy elements, sometimes collapsing into neutron stars or black holes. Each of these processes increased entropy. Each star that formed and burned was the universe moving from its low entropy initial state toward its high entropy final state. Each black hole that formed was entropy increasing. Even your life, your metabolism, your growth, your thinking, increases the entropy of the universe. The universe is in the middle of a long, majestic process of entropy increase. We are, in a deep sense, a byproduct of that process. Life emerges in the interesting middle state between extreme order and extreme disorder, in the region of intermediate entropy where complex, self-organizing structures can exist. Stars are not just burning balls of gas. They are entropy processing machines. They take the gravitational potential energy of their own mass and convert it into heat and light and heavy elements, increasing entropy in a controlled, sustained way that allows the universe to move from its special initial state toward its eventual maximum entropy future. And life, biological life, chemical complexity, consciousness, emerges in the vicinity of stars precisely because stars create flows of low-entropy energy, sunlight, that can be harnessed by self-replicating systems to maintain and increase their own complexity. We are, in the most fundamental sense, children of entropy. We exist because the universe is in the middle of becoming more disordered. We are the universe processing its own transition. This is not a nihilistic view. It is, I think, a profound and humbling one. We are not accidental. We are not random. We are the inevitable consequence of a universe that started special and is becoming ordinary. The process of becoming ordinary is the source of all the beauty and complexity we observe. But none of this answers the question of why the early universe was special. Why were the initial conditions so ordered? There are several proposals. Let me walk through the most scientifically serious ones. The first is simply that we live in a universe that happens to have low entropy initial conditions, and we should not expect an explanation beyond that. This is called the anthropic argument. In universes with high entropy initial conditions, or with no significant entropy gradients, there would be no stars, no planets, no life, no observers. The very fact that we exist to ask the question selects for a universe with low entropy beginnings. This argument has a certain logical force, but many physicists find it unsatisfying. It seems to give up on the search for a deeper explanation. The second proposal involves a model called the Hartle-Hawking no-boundary proposal. This is a framework in quantum cosmology, developed by James Hartle and Stephen Hawking, in which the universe does not have a classical initial state at all. Instead, the beginning of the universe is described by a quantum wave function that has no boundary in time. The temporal dimension of spacetime rounds off smoothly, like the geographic South Pole, where there is no edge, no boundary, no initial singularity. In this framework, the initial low entropy of the universe could, in principle, emerge naturally from the quantum state of the cosmos. The universe's beginning is a quantum event, not a classical one, and the thermodynamic arrow of time emerges from the structure of that quantum state. This is a beautiful idea, but it is not yet a complete theory. The mathematical details are difficult, and there is ongoing debate about whether the Hartle-Hawking proposal actually succeeds in explaining the low initial entropy. A third proposal involves the inflationary model of the early universe. According to inflation, a theory developed in the early 1980s by Alan Guth and others, the universe underwent a period of extraordinarily rapid exponential expansion in the first tiny fraction of a second. This expansion smoothed out any initial irregularities, diluted any initial particles, and left the universe in a very nearly uniform, very low entropy state. Inflation is now very well supported by cosmological observations. The cosmic microwave background radiation, the afterglow of the Big Bang, observed in detail by satellites like WMAP and Planck, shows precisely the pattern of fluctuations predicted by inflationary models. But inflation does not entirely solve the initial entropy problem. It pushes the question back: what were the initial conditions of the inflaton field, the field that drove inflation? Those initial conditions would themselves need to be explained. The fourth proposal, more speculative, involves a multiverse. In many versions of eternal inflation, our observable universe is one of an enormous, perhaps infinite, number of bubble universes, each with different physical properties and different initial conditions. In this framework, the low entropy of our universe is explained anthropically. We exist in a bubble where conditions permit life and complexity, and those conditions include a low entropy beginning. A fifth proposal comes from a cosmologist named Roger Penrose. His hypothesis, called conformal cyclic cosmology, suggests that the universe goes through an endless series of cycles, aeons, each beginning with a low entropy Big Bang and ending in a high entropy heat death. The key insight is that, in the far future of the universe, when all matter has fallen into black holes, and those black holes have evaporated via Hawking radiation, the remaining radiation in a vast, expanding, empty universe becomes conformally equivalent to a new Big Bang, the low entropy starting point of the next aeon. In this picture, there is no first moment. There is no special initial condition that needs explaining. Each aeon's high entropy end becomes the next aeon's low entropy beginning, through a mathematical transformation called conformal rescaling. Conformal cyclic cosmology is a fascinating proposal, but it remains controversial. It makes specific predictions about signals in the cosmic microwave background, so-called Hawking points, that could potentially be tested, and the evidence to date is ambiguous. So we do not yet have a consensus explanation for the low initial entropy of our universe. The question remains open, and it is one of the most important open questions in cosmology. What we do know is this: the low initial entropy is there. It is a real feature of our universe, and it is, in the current scientific understanding, the ultimate source of the arrow of time. Let's take one more look at the fundamental equations, because there is a subtlety we haven't fully addressed, and it matters for completeness. We have said that the fundamental laws of physics are, to a very good approximation, time-symmetric. But there is a small exception, the weak nuclear force, and we should understand what that exception means. In the 1960s, physicists studying the decay of particles called kaons discovered a small violation of CP symmetry. CP symmetry is the combination of charge conjugation, swapping particles for antiparticles, and parity, reflecting the universe in a mirror. In a universe that is CP symmetric, particles and antiparticles should behave in mirror image ways. Kaon decay violates this. The decay rates of kaons and their antiparticles are slightly different, and by a theorem called the CPT theorem, one of the most fundamental results in quantum field theory. A violation of CP symmetry implies a violation of T symmetry, where T stands for time reversal. So the weak nuclear force is, to a very small extent, not time symmetric. Its fundamental interactions are slightly different when time is reversed. This is a genuinely fundamental asymmetry. It is not a statistical effect. It is written into the laws themselves. Does this explain the arrow of time? Does this small t violation give time its direction? The answer, unfortunately, is no. Or rather, not entirely. The CP violation in kaon and B meson decays is real and important, but it is far too small to account for the overwhelming thermodynamic arrow of time, the irreversibility of a breaking egg, the spreading of gas through a room, the death of stars, the aging of living beings. None of these is significantly influenced by the T violation in the weak force. The CP violation does, however, play a crucial role in a different but related question. Why is there more matter than antimatter in the universe? According to our best understanding of particle physics, the Big Bang should have produced equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other, leaving only energy. If the universe had started with exactly equal amounts, all the matter and antimatter would have annihilated, and we would be left with a universe of pure radiation. No atoms, no stars, no people. But we do exist. There is matter in the universe. The small asymmetry in the decay rates of matter and antimatter particles, due to CP violation, produced a small excess of matter over antimatter in the early universe. When the annihilation was complete, that small excess, roughly one extra proton for every billion proton-antiproton pairs, was all that remained. And that small excess is us. The atoms in your body, the Earth, the stars and galaxies, all of it is the leftover residue of a tiny asymmetry in the laws of particle physics. The CP violation in the weak force, then, is responsible for the existence of matter. But the arrow of time, the direction from past to future, the reason entropy increases in one direction, traces back to the low entropy initial conditions, not to the CP violation. These are two separate asymmetries. One is an asymmetry of the laws. CP violation explains why matter exists. The other is an asymmetry of initial conditions. The low entropy of the early universe explains why time has a direction. Both asymmetries are real, both are important, but they are distinct, and they explain different things. There is, however, a philosophical connection. Both asymmetries, the matter-antimatter asymmetry and the entropy asymmetry, trace back to the Big Bang. They are both features of the initial state of our universe. They are both part of the extraordinarily special character of that beginning. And this suggests that the arrow of time and the existence of matter may be connected, at a deep level, as aspects of a single, coherent story about the origin and nature of our universe. A story that we are only beginning to read, and if this deep, patient exploration of time and physics feels right for you, if Science for Sleep is the place you come to let difficult ideas settle gently into your mind, we would love for you to be part of our community. Subscribe and join us on every journey. We have touched on time dilation, the slowing of time due to velocity and gravity, and now let's go deeper into it. Let's explore what extreme time dilation means in practice, and what it tells us about the structure of time. We established that time runs slower when you are moving quickly relative to another observer. This is special relativistic time dilation, and time runs slower the deeper you are in a gravitational field. This is general relativistic time dilation. Let us now consider some extreme cases. At the surface of a neutron star, the gravitational field is roughly 100 billion times stronger than at Earth's surface. A clock on the surface of a neutron star would run significantly slower than a clock in free space far away. If you could somehow stand on the surface of a neutron star, which you couldn't because the tidal forces would tear you apart, and the surface gravity would crush you instantly, time would pass more slowly for you than for a distant observer. Now consider the surface of a black hole, the event horizon. As you approach the event horizon, the gravitational time dilation increases without limit. To a distant observer, your clock appears to run slower and slower, approaching a complete stop as you reach the horizon. From the distant observer's perspective, you take an infinite amount of their time to cross the horizon. But from your own perspective, you cross the horizon in finite time. Your own clock ticks normally. You experience time passing at its usual rate. The crossing is unremarkable, at least for a large black hole. This is because time dilation is a relative concept. It describes the ratio between the time experienced by two different observers. From the distant observer's frame, your time is dilated. From your frame, the distant observer's time is compressed. Once inside the event horizon, time takes on a new character. As we discussed earlier, the radial direction, pointing toward the singularity, becomes time-like. This means that moving toward the singularity is not moving in a direction in space. It is moving in the direction of time. The singularity is in your future, and there is no way to avoid your future. The concept of time inside a black hole stretches our intuition to the breaking point. There is no way to stand still, in the sense of not moving toward the singularity. Doing so would be like trying to stop time from passing. It is not a mechanical constraint. It is a geometric one, built into the very structure of space-time. The mathematics tells us that the proper time, the time experienced by an infalling observer, between crossing the horizon and reaching the singularity, is finite and calculable. For a black hole of one solar mass, it is about 10 microseconds. For a supermassive black hole with a mass of 1 billion suns, it might be several hours. The larger the black hole, the more time you have between crossing the horizon and reaching the singularity, because the curvature at the horizon is gentler, and at the singularity, our equations break down. Time, as described by general relativity, ceases to be a well-defined concept at the singularity. This is one of the signals that general relativity is incomplete, that a deeper theory is needed. Many physicists believe that a quantum theory of gravity would replace the singularity with something else. Perhaps a region of extreme but finite quantum geometry. Perhaps a bounce, where the infalling matter passes through a phase transition and emerges into another universe, or another region of space-time. These are speculative possibilities, but they are taken seriously by researchers working on quantum gravity. Now let's think about time dilation from the opposite extreme. The very fast-moving objects of special relativity. If you were to travel at 99% of the speed of light, time would pass for you at about 1/7 the rate it passes for a stationary observer. If you traveled at 99.9% of the speed of light, time would pass for you at about 1/22nd the normal rate. At 99.999% of the speed of light, time dilation would be so extreme that for every year you experienced, more than 1,000 years would pass on Earth. This is not a thought experiment. This is what the mathematics of special relativity tells us. For any massive particle, anything with mass, the speed of light is an asymptotic limit. You can get arbitrarily close to it, but you cannot reach it. And as you approach it, the time dilation becomes arbitrarily large. Photons, particles of light, move at exactly the speed of light. What is time like for a photon? This is a subtly tricky question, because the concept of a rest frame breaks down for a massless particle. A photon does not have a rest frame, but in the formal limit, as velocity approaches the speed of light, the time dilation factor approaches infinity, meaning that for the photon, no proper time passes between its emission and its absorption, regardless of how far it travels. In a sense, a photon exists in a kind of eternal moment. It is created and destroyed in a timeless instant. This is not quite right as a literal statement. The concept of duration doesn't apply to a photon in the same way, but it captures something true about the geometry of light's path through space-time. The fact that light travels at the same speed for all observers, regardless of their own velocity, is the foundation of special relativity. It is empirically confirmed beyond any reasonable doubt, and it leads directly to the time dilation that we have been discussing. All of these relativistic effects, time dilation, length contraction, the relativity of simultaneity, arise from the single postulate that the speed of light is constant and universal. And from that single postulate comes a complete reworking of our concepts of space, time, and simultaneity. But notice, none of these effects reverses the direction of time. Clocks run slow, but they still tick forward. A traveler moving near the speed of light ages more slowly but still ages. Time is dilated but not reversed. The arrow of time is robust against relativistic effects. It is preserved in all reference frames. Every observer, no matter how fast they are moving or how deep in a gravitational field they are, still experiences time moving from their personal past to their personal future. This is a deep consistency. The relativistic framework, which makes time so relative, so observer-dependent, so intimately linked with space, nevertheless preserves the one thing that is universal: the direction of time. We have now built up a rich understanding of time, from thermodynamics and entropy, through the statistical nature of irreversibility, through the relativistic structure of spacetime, and into the extremes of black holes and quantum mechanics. Now let's address directly the question that may have been in the back of your mind throughout. Could time ever run backward? Not just locally or statistically, but genuinely, fundamentally backwards, in a way that would be observable, meaningful, and physically real. Let's think about this carefully. In thermodynamics, the second law tells us entropy increases, but it is a statistical law. There is a non-zero probability, an unimaginably small one, that entropy could spontaneously decrease in an isolated system. If that happened in a small region of space, would that region be experiencing time running backward? From the outside, looking in, it would look backward. A film of that region played forward would look like a film of a normal region played backward. The events in that region would be entropy decreasing rather than entropy increasing. But from the inside, for an observer within that region, if such an observer could exist and could be aware, the direction of their psychological time would also be reversed. Their memories would record the final state as the past and the initial state as the future. Their sense of cause and effect would be reversed. So the question of whether they are experiencing time backward depends on whether you define forward relative to the larger universe or relative to their local arrow of time. This is a profound ambiguity. It suggests that the direction of time is not an absolute feature of reality, but is, in some sense, defined by the local thermodynamic environment. Now, in practice, you will never encounter a region of the universe where entropy is spontaneously decreasing on a macroscopic scale. The probabilities are simply too small. But in principle, the possibility is there. There is a more serious physical scenario worth considering, though. It involves the laws of physics themselves and the concept of CPT symmetry. CPT symmetry is one of the most fundamental symmetries of quantum field theory. It states that the laws of physics are invariant under the simultaneous combination of C, charge conjugation, swapping particles and antiparticles, P, parity, spatial reflection, and T, time reversal. This is not just an empirical observation, it is a theorem derived from very general assumptions about the structure of relativistic quantum field theory. What CPT symmetry tells us is this: If you take any physical process, swap all particles for antiparticles, reflect it in a mirror, and play it backward in time, the result is an equally valid physical process. This means that the time-reversed version of any process is physically possible, but only if you also swap matter for antimatter and reflect in a mirror. A time-reversed universe, one where time runs backward, would look like our universe, but made of antimatter and reflected in a mirror. All the physical processes would be equally valid. The laws would be unchanged, but we are not living in an antimatter universe reflected in a mirror. We are living in this universe, with this particular matter and this particular chirality. And in this universe, with these initial conditions, entropy increases in the forward direction of time. CPT symmetry does not allow time to run backward in our universe as we find it, but it tells us that a time-reversed CPT conjugate universe is theoretically valid and would be indistinguishable from ours if you were inside it. This is a beautiful and strange thought. There is, in the CPT sense, a version of the universe that is the mirror image of ours in time, space, and charge. Some physicists have proposed that our universe and its CPT conjugate are both real, that they are two sides of a single quantum event, a kind of pair production of universes from the quantum vacuum. In this speculative picture, sometimes called the two-sheeted universe or the CPT symmetric universe, the Big Bang is the moment of creation of both our universe, moving forward in time, and its mirror universe, moving backward in time. From our perspective, both universes have increasing entropy in their own forward temporal directions. Both are consistent with the CPT symmetry of the fundamental laws. This is a fascinating theoretical possibility, but it is highly speculative and not yet testable in any direct sense. For practical purposes, for the purposes of understanding the world we actually live in, time does not run backward. Entropy always increases. The past is fixed, the future is uncertain, and the arrow of time is real. But the fact that the laws of physics permit a time-reversed universe, that the equations don't in principle forbid it, is a reminder that the arrow of time is a feature of our particular universe's history, not a logically necessary feature of all possible universes. We have been circling around a question that is both scientific and deeply personal. Why do we remember the past and not the future? We touched on this early in our journey, but now, with all the thermodynamic and relativistic context we have built up, we can answer it much more deeply. Memory is a physical process. It is a pattern encoded in the physical structure of a brain, in the connections between neurons, in the chemical states of synapses, in the electrochemical signals that flow through neural circuits. A memory is information about a past event, stored in a physical medium. For a memory to form, the brain must undergo a physical change that is correlated with an external event. The external event causes, directly or indirectly, a change in the physical state of the brain. That change persists, and later, the brain can re-access that changed state, can retrieve the information, and reconstruct a representation of the original event. This process, cause leading to correlated physical change, is thermodynamically irreversible. When an event occurs, it leaves traces in the world around it. Heat is released, particles scatter, information spreads. These traces are the physical record of the event, and they accumulate in higher entropy configurations. A memory is exactly this: a physical trace of a past event, persisting in the low entropy brain, surrounded by the higher entropy traces of the event's effects on the environment. Why do we not form memories of future events? Because memories are physical correlations established by the causal influence of an event on the physical state of a brain. Future events have not yet caused any physical changes. They have not yet scattered any particles or released any heat or established any correlations. The future is not yet causally embedded in the present. The past is. This is the thermodynamic reason for the asymmetry between memory of the past and ignorance of the future. But there is a deeper point here. The very concept of prediction, of reasoning about the future, depends on records of the past. We predict the future by using knowledge of the past, knowledge encoded in memories and records, which are themselves physical traces of past events. All of our knowledge of the world is, in a fundamental sense, knowledge of the past. Even our knowledge of the present, what we see, hear, feel right now, is slightly delayed. Light takes time to travel from objects to our eyes. Sound takes time to travel to our ears. Neural signals take time to travel to our brain. Our experience of the present is always slightly in the past, and our anticipation of the future is built entirely from this backward-looking knowledge. We predict the future by extrapolating from the past. We have no direct access to the future, not because the future is hidden from us, but because the future has not yet causally influenced us. It has not yet left traces in the world we inhabit. This is the thermodynamic basis of the phenomenology of time. The pastness of the past, its fixed, unchangeable quality, is a consequence of its higher entropy and the irreversibility of the physical processes that created our records of it. The openness of the future, its uncertain, contingent quality, is a consequence of the fact that the future has not yet made its entropy-increasing imprint on the world. Memory, knowledge, causation, agency, experience, all of these are thermodynamic phenomena. They arise because we live in a universe that started in a low entropy state and is moving toward higher entropy. The flow of time that we experience, the sense of moving from past to future, is the subjective aspect of this objective thermodynamic process. We are not experiencing time. We are experiencing entropy. This is perhaps the most profound insight that thermodynamics offers about the human condition. The feeling of being alive in time, of being here, now, this moment, this breath, is not separate from the laws of physics. It is those laws. It is entropy, experienced from the inside. Take a moment with that. The breath you feel right now, the quiet weight of your body, the gentle drift towards sleep, or toward alertness, depending on how this evening finds you. All of it is the universe's entropy doing its work. All of it is the arrow of time, experienced from within. And if that thought brings any peace, if there is something comforting in the idea that your experience of time is woven into the very structure of the universe, then let that thought rest with you for a while. We have traveled far. We began with a simple, seemingly obvious observation. Time moves forward, always forward, never backward. And we asked why. We found that the answer is not written in the fundamental laws of physics. Those laws are, to a very good approximation, time-symmetric. They work equally well in both directions. The direction of time is not a consequence of any fundamental asymmetry in the equations. The direction of time is a consequence of the initial conditions of the universe. The Big Bang, that extraordinary, still mysterious beginning, produced a universe of very low entropy. Low entropy in the gravitational sense. Matter spread nearly uniformly, with gravity not yet having done its work of pulling things together into stars and black holes. And from that low entropy beginning, entropy has been increasing ever since. The direction of increasing entropy is what we call the future. The direction of lower entropy is what we call the past. This is the thermodynamic arrow of time. We met Ludwig Boltzmann, who gave entropy its precise mathematical meaning. Entropy is the logarithm of the number of microscopic arrangements that correspond to a given macroscopic state. High entropy means many possible arrangements. Low entropy means few. And the second law of thermodynamics, entropy increases, is not a fundamental law, but a statistical certainty, the overwhelmingly probable behavior of systems with enormous numbers of particles. We explored how this statistical irreversibility, while not absolute in principle, is so extreme in practice that it is indistinguishable from a genuine law. The probability of entropy decreasing spontaneously on a macroscopic scale is so small that it will never be observed in the lifetime of the universe. We turned to Einstein and found that time is not a universal backdrop, ticking at the same rate everywhere. Time is relative. It passes more slowly for fast-moving objects and more slowly in strong gravitational fields. Different observers measure time differently. The fabric of space-time is curved by mass and energy, and objects move through that curved spacetime along paths called geodesics. But even within this relativistic framework, the direction of time is preserved. Every observer, in every reference frame, experiences time moving from their personal past to their personal future. The arrow of time is robust against relativistic effects. We gazed into black holes and found time distorted beyond recognition. Near the event horizon, time dilation becomes extreme. Inside the event horizon, the singularity lies in the future of every path through spacetime. The direction of time becomes the direction of increasing curvature. pointing inexorably toward the singularity at the heart of the black hole. We encountered Hawking radiation, the quantum process by which black holes slowly evaporate, and the profound puzzle of the black hole information paradox, where the question of whether information is preserved or destroyed connects to the deepest questions about time reversibility at the quantum level. We looked at the quantum perspective and found that decoherence, the process by which quantum superpositions become effectively classical, is itself an entropy-increasing, irreversible process in the statistical sense. The quantum mechanical arrow of time traces back, once again, to the low entropy initial conditions. We asked why the early universe had such low entropy, and found that this remains one of the deepest open questions in cosmology. Various proposals, inflation, the Hartle-Hawking no-boundary condition, cyclic cosmologies, the multiverse, offer partial answers but no definitive resolution. The mystery of the initial conditions remains. We considered whether time could run backward, and found that while the laws of physics permit it in principle, the thermodynamic probabilities make it operationally impossible in any meaningful sense. The direction of time is not forbidden in the fundamental laws, but it is overwhelmingly enforced by the statistical behavior of large numbers of particles starting from low entropy initial conditions. And we connected all of this to the deeply personal experience of time, to memory, to causation, to the feeling of being alive in the present moment. Memory is a physical trace of past events, established by irreversible entropy-increasing processes. The openness of the future is the absence of such traces. The flow of time is entropy, experienced from the inside. What does all of this mean? There is a temptation to find the thermodynamic view of time cold, or reductive, or somehow diminishing. If the arrow of time is just entropy, if the feeling of being alive in the present moment is just the universe's disorder increasing, does that make our experience less real, less meaningful? I think the answer is no. And I think the reasoning is worth sharing. The fact that your experience of time is connected to the laws of thermodynamics does not make that experience less real. It makes the connection deeper. It means that your sense of being here, now, this moment, your awareness of the passing of time, your memories of the past, your hopes for the future, all of this is written into the structure of the universe. You are not separate from the laws of physics. You are those laws, expressing themselves in a form that can wonder about themselves. The universe began in a state of extraordinary order. Over 13.8 billion years, entropy has been increasing. Stars have formed and died, galaxies have assembled, planets have cooled and oceans have filled, and life has emerged and evolved. And here, at this particular point in the long arc of cosmic entropy increase, you are a local, temporary, intricate reduction in entropy, a pocket of complexity and order sustained by the flow of low entropy energy from the sun, surrounded by the increasing entropy of everything around you. You are the universe maintaining a small region of low entropy just long enough to become aware of its own thermodynamic story. And the story you are aware of, the story of time moving forward, of the past being fixed and the future being open, of memory and anticipation and the irreversible flow of moments, that is not an illusion. It is the most direct experience you have of the most fundamental feature of the universe you inhabit. Time moves forward because the universe began in a special, low-entropy state and is moving toward a high-entropy future. Every breath, every heartbeat, every thought and memory and hope and loss, all of it is the universe doing what it must, becoming more disordered, more dispersed, more uniform, moving from the extraordinary beginning toward the quiet end. And in the middle of that journey, in this thin, bright moment of complexity and awareness and life, you exist. That is not a small thing. That is everything. The second law of thermodynamics tells us that entropy increases. It does not tell us that beauty decreases. It does not tell us that meaning decreases. It does not tell us that love or music or the particular quality of light at dusk or the feeling of a hand in yours in the dark. It does not tell us that any of these are less real because they arise from particles and probability and the statistics of enormous numbers. It tells us that they are real precisely because they arise from particles and probability and the statistics of enormous numbers, that the universe has found a way, in this extraordinary middle passage between low entropy and high entropy, to be aware of itself, to wonder, to ask why time moves forward, to sit quietly in the dark and listen to someone explain entropy. And we, all of us, together, are that awareness. Let your mind rest now on what we have covered. The second law of thermodynamics. Entropy always increases. The low entropy of the Big Bang. The extraordinary specialness of our beginning. The relativity of time. Its flexibility. Its dependence on velocity and gravity. Its deep connection with space. The arrow of time. Not a fundamental law, but an emergent consequence of where we came from. Black holes and the extremes of time dilation. The singularity as a time, not a place. Hawking radiation, and the preservation of information at the quantum horizon. And memory, and causation, and the experience of being alive in time. All of it woven from the same thermodynamic thread. Time moves forward because the universe remembers its extraordinary beginning. We move forward in time because we are made of the universe's matter, shaped by its laws, carried along by its increasing entropy. We are time, becoming aware of itself. And the forward direction. The direction we all feel, the direction we cannot reverse, the direction that carries our memories behind us and our futures ahead, is not an accident. It is not an illusion. It is the signature of a universe that was once astonishingly ordered and is becoming, slowly and beautifully, something else, something we are still in the middle of discovering. Close your eyes now if you haven't already. Feel the breath moving through you. Feel time, doing what it always does, moving forward as it always will. Thank you for spending this time with Science for Sleep. If this journey through entropy, relativity, black holes, and the nature of time felt like the kind of deep, patient science you want more of, subscribe to Science for Sleep. Every night, we go deeper. Every night, we slow down and ask the questions worth asking. Sleep well. The universe will still be here in the morning, and it will still be moving forward.